Okay, and this last part of the morning session, we have reserved a bit of time to discuss the evaluation metrics. And I think, let me see. And so, you know, this is, and Mike will talk more about it. We're going to sort of co-moderate this session. Do you want to come on up and lead it, Mike? I think that's good.
Thank you.
Yeah.
I think one way or another we'll collect some notes on this.
Yeah.
Okay. And I'm not quite sure why we didn't have this discussion at a prior workshop, because it's sort of fundamental to asking, well, which methods work better? You know, how do you evaluate that? And questions keep coming up. There are some favorites, which I have up here. I don't know if we're going to answer them, but at least maybe everybody can have a chance to hear the arguments on all sides. And maybe there's some new methods that could also be useful. I guess the other thing is that there is, a saying that from the early days of optical microscopy, that the biggest debates are just beyond the resolution of our instruments. And I think we may be a little bit in that situation here. Maybe as we get more statistics and methods get closer, it'll become, we won't have to worry quite so much about whether the difference between two things is statistically significant. But I think this is important. I guess I could start off by pointing out my favorite issues, but I wouldn't mind maybe just opening up to you guys and say, what are your favorite issues and what are your, bees in your bonnet or whatever. John.
What the impact that this tool would have on my projects, and how would I turn some statistic into some predicted measure of that, and what is the cost of using this tool? I don't know.
You know what? Would it be okay to have people come up and use this microphone? Because that's gonna be. Oh, there's one back there. Is that one gonna go to the webinar? Well, okay. Why don't we? We're gonna, to those of you who are on the webinar, we're gonna try letting you hear this via the public address system. I'm not sure that'll work, but please tweet or let somebody know. By chat, I guess, if you can't hear the question. John Codera again.
So just to summarize, the biggest question in my mind are, how do I use statistics that gives me some idea of what the impact of actually using a tool in services or projects might actually be, how much will it actually help? And then what's also the cost of applying that tool in terms of, I'm not sure we're really capturing any information relative to the cost in terms of CPU hours or other
Yeah, so just to recapitulate, because I'm not sure how well that came through, but basically a pragmatic metric would be how well does a given method advance a project? Like that should be the ultimate criterion, a drug discovery project, and at what cost? So some trade-off of cost and benefit. Are there any thoughts on that, or? John Bowman.
I agree.
John Bowman agrees. Okay. But I mean, is there a way to, is there a surrogate for that? Do the numbers we have, are those adequate surrogates, or should we be thinking?
Well, so far, all the numbers we've seen this morning, there hasn't been a metric of how much computational effort did one method take versus another.
Yeah, so there was no. One of the comments is that we have no information on the computational effort of these things. So we do have information on some RMSDs and Spearmans, but we don't know how the cost at this point. So that may be something to think about for future rounds.
The only thing I can see happening is that having enough data accumulated processing through the database system or computer data, we can build a statistical model of what a simple predicted drug discovery project might look like.
Right.
At least for a target class. And then come up with a statistic that can be used as a surrogate for how well a model might actually perform in a statistical sense in that statistical model. That's the only thing I can see working is translating this into actual impact. And then you can make value-based decisions depending upon what your utility function is in terms of cost, time, money, personnel, things like that.
So if I could, I mean, in a sense, we'd be asking a pharmaceutical company to give us a full dump of a project, in a sense, including all the compounds that were disastrous, and then say, okay, if we applied one method and sort of did a, choose your plot kind of story down that, how would that compare? That's interesting. So you're saying one wouldn't need to release the data publicly as long as somebody is willing to run it in a confidential setting. Interesting.
I think that sounds great, but I think it's almost impossible to do in practice. It would be incredibly expensive. The closest thing I can think of is there was a paper that was published last year by Roche, where they did a very small comparison on one program where they had a set of chemists just operating in isolation, making compounds. They had chemists doing sort of standard structure-based design, and then they had FEP. And in that case, FEP considerably outperformed the other methods. But I think in practice, things tend to bleed over, right? And it's always a combination of medicinal chemist insight plus computation plus just your empirical knowledge from reading the literature. But I think just in terms of back to your earlier point of what's useful, right? And I mean, my view of this from 22 years of doing this is typically, if you can dock and you can get within 2 angstroms, that usually tells you whether something's reasonable. For activity prediction, it depends on where you are in the project, but it's probably going to be somewhere between 5 and 10-fold. And I think, if you just think about this sort of medicinal chemist sort of mental inhibitor math, I think a good medicinal chemist can tell you within 10-fold what the change in the molecule is going to be. So we've got to be able to do better than that.
So if I could, that was Walter's, so that if you have an RMSD less than 2 angstroms, that's going to be useful for pose prediction, and affinity to better than, let's say, a factor of 5, IC50, that can be useful. So regarding the pose predictions, if less than 2 is the criterion, should we, instead of be using RMSD, means and medians, should be using fraction predictions that are less than 2.5? Would that be a superior metric?
It's hard though, right? Because then you're throwing some hard cutoff and you've got things that are
Indeed.
If we could come up with some data.
Okay. I think there was somebody over there, and then John. I think there was somebody before. I'm sorry.
I'd like to raise another question about how it's important to maybe we can remove from the analysis the crystal structures that have inter-subunits interactions, because I consider that this is not pertinent for the solution structure and probably for affinity. So this is
right. That's basically removing ligands that have large inter-subunit contacts. I think what we another piece of that maybe that we talked about a lot with Nisha and Mill was removing atoms which had lousy electron density from the RMSD calculation. And my impression, Mill, I don't know, is that even the ones that had crystal contacts, that might have been problematic. The core of it was still in a reasonable place that was interpretable. So maybe we could not throw out the entire ligand as a challenge, would throw out parts that we thought were either had lousy electron density or were impacted by a contact, just as a thought. Well, that becomes a judgment call. I think John was next. Thanks.
Just as a substitute for total energy or CPU time, would it be possible just to have a stage 1 that was further divided where the time cutoff was shorter? So you were allowed maybe for stage 1A 2 weeks, something really short.
Interesting.
Or 3 weeks, and you could submit it at any time. You wouldn't have any answers. You would just have cutoff dates.
That's interesting. Yeah. So basically, a time stage challenge where from the moment the data package is released, you have 1 week to turn your numbers, 2 weeks to turn your numbers, or whatever, so that you can see who can do it quick. And it might depend to some degree on who has a big computer cluster, right? But you can see there. Mm-hmm.
So let me address this first one, because one of the complications that many of us have is I can't do a prediction in 2 weeks if I'm out of the office, those 2 weeks. You know, so there's a fundamental problem there, scheduling everyone's time where we're all free at the same time, so it's fair. And it has been a real problem for at least OpenEye because our worst travel time is exactly when the challenge opens. And so the only reason that we were able to participate this year is because I worked over a weekend. And you know, that's just not, I appreciate this and I like the suggestion, but how we do this so that it actually works out practically. I'd like to go back to Pat's comment of, you know, a percentage less than 2 angstroms, and I will apologize for propagating that at least in some part. The 2 angstrom problem. We recognize fundamentally that 2 angstroms tends to work, and it's a nice rule of thumb. And you know, if we all went on the Pinsky criteria for docking, that's a nice one. But of course, and Pat will agree with this, if we're doing small molecules, if we're doing less than 350 molecular weight, 2 angstroms is basically wrong. And if we're doing molecules like was in CAT-S, 2 angstroms is probably not broad enough because the molecules are so large. So I've always had a problem with that. I did experiment with trying to use real space correlation coefficient values. That's not worked out well, at least all the work that I did, unless one looks at, and Steve Burley could probably comment on this, unless one looks at decently generated minute maps, that might be a metric by which we can use that as a way of calculating the correct pose. One of the things that I've also looked at is actually having a fluctuating RMSD criteria, and that is look at the precision of the structure. If I have a 6 angstrom resolution structure, 2 angstrom prediction is basically nonsense. The quality of that structure is too high. And so maybe having a sliding RMSD criteria that goes with the precision of the structure. And that's one of the things we played with in the past as well. So a 3 angstrom structure, well, it shouldn't, you know, 2 angstroms is probably not broad enough. So that's just a couple of the stream of consciousness.
Cool. So just to respond to a couple of things, your point about the timing is I agree with. So that's pretty clear. The real space correlation coefficient, we've looked at that also when we found some quirks in it that I didn't understand, which is you could have a structure that was like every atom was shifted by a small amount relative to the electron density. It would look like a hideous result. Whereas if you had it didn't seem to scale intuitively. And then I think another thing you said was that the RMSD should be reinterpreted both in terms of the size of the ligand and in terms of the resolution of the structure. Resolution of the structure, I think we're kind of okay with that because we just have been remaining within 2.5 angstrom resolution structures that will allow. Size of ligand is an interesting one to think about. Thanks for that. Chris.
Could we ditch RMSD and instead ask how well do the predicted poses fit the density?
Oh, sure, but what metric? I mean, would you do?
Well, I guess you could do imagine different times overlap with density, things like.
Oh, how well it fits. Now, one thing we ran into with how well it fits the density is you can have a fairly symmetric looking structure where two flops of the ligand will fit the density equally well. One of them makes a logical set of hydrogen bonds and the other one doesn't. And we found ourselves struggling with the sort of, you know, epistemological question of whether to weight those. Exactly.
Sense, but the observable that we're actually comparing to is the density. So that was one point that I'm just I'm not saying, I'm just another thought is the point is earlier on getting more compounds from companies, getting compounds that did not perform well, getting disastrous compounds. I think this is a great idea. Now, when your bullet point there, greater than 10 micromolar, for example, the assay data, when companies take a compound that doesn't fit their expectations, they tend, because it's not potent, they tend not to report it, number one. They tend not to measure a gain, that's number two. And number three, it can be outside the assay data. So compounds that perform poorly, you tend not to see them and the experimental data tends to be thin on the ground.
Well,
I think they're very important.
Compounds that perform poorly. I will tell you that the ones that were greater than 10 micromolar are ones from the assays that we commissioned. And so we did have an expectation that those would be something interesting in some way. So those were definite fails, unfiltered.
That would be really important because you make the compound generally, if you make it, you expect it to be good. So I think we can take it as inferred and inferable. And if we can predict that, I can tell you I had a whole lot more success at my former company in trying to predict and saying if you make this compound, it will be bad.
Interesting. So the goal of predicting failures.
The return on investment was synthetic chemistry time not spent making compounds that would be bad.
Interesting. Yeah.
So including these in our assays in our sets would be good.
Right, and I think one of the things that Pat raised in interpreting these, because we were struggling with what to do about those for the rankings, is to do a categorization, and that I think that would help capture what you're talking. Romy, what time is? Okay, so are there any other, as Romy would say, burning issues that somebody wants to raise, or do you want to go through these? The last one, the raw submitted files. Yeah. Okay. So this is something I mentioned before as well. Is that, I think, you may prefer median to mean on the RMSD or the way around. You may want to not use rankings of the 10 micromolar ones since there's sort of just a hard cutoff on the assay, which is why we put the raw submissions from participants on the website. So you are welcome, you and others are welcome to download those and do your own analyses. So, we're not claiming to be the be all and end all of how to do it. And we'd love to have other people's insights.
Just something that came up I wanted to comment. I believe that for the green predictions, there's many compounds that have exactly 50 micromolar, or maybe it's 10 micromolar or something. I doubt that they're all exactly that. Like there's often, and we look at
those are the greater than 10, I think.
Yeah, so that's just going into the green predictions. Maybe we should think about those compounds being a little differently.
Yeah.
Because obviously you shouldn't correlate to that threshold number.
Right, that was why I mentioned, that's why Pat got us into, so I believe that for the ranking statistics, so we've ended up throwing those out. So they're not, so there was a revision. We say what's on the website is provisional. One of the things that we provisioned or whatever was we threw out those and redoing the Kendall's tau rankings and experiments. And also what Pat has suggested and is not up yet is a categorical, did you get, what was it, several different levels of active or maybe you'd call that inactive. So we agree with those concerns.
Yeah, it's kind of a lot of that. We're having the binding determination, virtual screening, here's 1,000 compounds, only 50 work, and you identify those. I think that also,
yeah.
We did kind of try to do that HSP 98 in the first challenge, it wasn't quite enough data. But that would really get to, value to the company because we're actually creating enriched sets.
Excellent. Okay. Thank you. Well, it seems like there's a lot more to talk about, so it potentially could pick it up again if conversation flags tomorrow. Okay.